Hello everyone, welcome to day 24th of January Leetcode challenge, and today's question is merged k sorted list. So in this question you are given sorted list that are k in number, and you need to return the merged output of all those lists, that is 2, in a sorted manner. For example, this is the first list 1 4 5, then 1 3 4, then 2 6. The output should be the amalgamation of all these three lists, that too in the sorted manner. How can we do this question? We will be using our previous knowledge where we did the question for merging two sorted lists in the past on January 4th. That was on Jan 4 2021. And whatever we learned there, we'll be utilizing exactly the same concepts to extend this to k list. And will be solving it using the priority queue approach, which is a new approach for all of you. So let's walk through the slideshow that I have created, and let me just start the slideshow. Merge case sorted list. So let's break the problem into two parts. The first part is exactly the repetition of what I told at that time. Let's create a dummy pointer, dummy head for the new node, and this is for L1 and this is for L2. So let's iterate through these two lists. Which one is the minimum one? First one is the minimum one. Attach 1 and increment this pointer to next point position. Which one is the minimum one? 2 and 3 are equal. You can attach any of them. Let's attach 2 for that case. Attach 2 gets attached. Move ahead. We get 3 and 2, which is the minimum one. 2 is minimum one. Attach 2 again. Move ahead. The second point, this pointer moves ahead. And which one is the lower one? Any. So first one moves ahead. 3, we get 3. Then we get 4. Then which one is the lower one? 3. 3 out, 3 and 4th. 3 is the lower one. Attach 3. Move ahead. We get to the next position. L2 is here, L1 is here. Lower one is 4. Attach lower one. Done. Move ahead. 5. Which one is the lower one? 4 is the lower one. Attach 4. And move ahead. We get 8. L2 gets here. Which one is the lower one? 5 is the lower one. Attach 5. This is done, and let's attach everything what is remaining as part of the remaining list to the end of this. 8, 10 and 11. So this is how we merged two lists, given both of them are sorted in nature and the resultant list is also sorted in nature. Now let's extend this approach for the k list. How are we going to do this? We'll be using merge sort technique. Similar thing that we do in for an array, merge sort technique, where we merge uh, an array list or an k array list together. We are doing exactly the same thing here. So we will make pairs L1 and L2, L3 and L4, L5 and L6, L7 and L8. We'll merge them in pairwise. So we get L1 dash, L2 dash, L3 dash, and L4 dash. Then again we repeat the same process. We get L1 double dash, and here using L1 dash and L2 dash, and using L3 dash and L4 dash we get L2 double dash, and the final merger we get our final answer. So this should be our final answer. I'll be coding this up as my first approach so that you understand it better. It's not a complex approach, it's a simple approach to do once you know how to write the merge sort uh, algorithm. Let's talk about the other case now, where I'll be providing a BFS solution. So what you need to do, you maintain a queue and you add all the starting nodes of uh, all the k list into your queue. So 1, 2 and 3 gets added into the queue, and it's a queue responsibilities to pick up the one with the minimum value first. So which gets picked up? One gets picked up, and as soon as one gets picked up, you attach it to your uh, answer final output list. So one gets attached. We'll be using dummy pointer again. So -1 1, and then you will increment this list, put back this list to the end of the queue, pointing to the next node. So if this gets picked up, you add 2 to it. So this gets added, and you delete this. Again, out of these three, which one will be picked? The lowest one. Then this gets picked up, 1 again gets attached, and what we'll do, since this is this one, it will increment it to the add the next its next element to the end of the queue. So 2 gets added. Now we have 2 to 2, and what we'll do, pick up the lowest one. So since all are equal, pick any. So let's assume this was picked since it was added at the earliest position, and move ahead. So this gets added, 2 gets added, this gets deleted, 3 gets added to the queue, and 2 3 3 we get, and this 2 is this one. So add 2 again, lowest one is 2, add 3 back, so 3 gets added, and again pick up the lowest values among all the possible values in the queue. So we get 2, add 2 again, and move ahead. So this time you pick up this, and 5 gets added, and among these three, which one is the lowest one? 3 is the lowest one. So this 3 is gone, and move ahead. Then since it's null, so we'll not add it till its the next tail to the queue. And now we have 3, attach 3, move the pointer to the next position, add 4 to this. So this gets added, 4 gets added, and among these two, which one is the lower one? 4 is the lower one. So it's the responsibility of the comparator to give you the lowest value. I'll tell you how do we write that. So the trick lies with the comparator. So 4 gets added, 4 gets picked up. So now we have 4, and we add 8 to the end, and which one is the lowest one out of 5 and 8? 5 is the lower value, so 5 gets added, we add 5, and then it turns empty. Skip this list now, and we get 8, so 8 gets added. So this is how we iterate through the list, complete list. So now the list has 1 1 2 2 2 3 times, 3 3 4 5 8. So this is a new list, and this is an answer. So let me just code both the approaches up, and then I'll tell you about the space and time complexity, which one is the better one to go. Let's start with the first algorithm that we discussed, an extension to merging two sorted lists. So let me just write the helper method first, where we are merging two sorted lists and returning the merged head of the new list. So merge method, and it accepts head pointers for list 1 and list 2. If corner cases L1 equals to null, return L2. If L2 equals to null, return L1. And let's create a dummy node, new list node -1, and let's create a T for iterating over our resultant list, T1 for iterating over our L1 list, and list node T2 for iterating over our L2 list. What we will write, if while T1 is not equal to null and T2 is not equal to null. We have done this in the past. I'll share the video link. If you have any confusions, you can refer there, but it's not complicated. If you have gone through that video in the past, if L1 is less than L2, we'll choose up the lower value, L dot next equals to T1, T equals to T dot next, T1 equals to T1 dot next, else again the same thing with then L2 pointer, otherwise we'll choose the L2 value. So L2 gets attached, this gets T will definitely be incremented, and moving, since we chose T2 value, T2 gets incremented. Again, since one of the list has exhausted and one is still there, so assuming that T2 got exhausted, writing the follow-up code here. Now assuming the same thing, that T1 got exhausted, writing the follow-up code here. And this is for the part where T2 got exhausted and T1 is still there, and this is for the part where T1 got exhausted and T2 is still there. Return dummy dot next. Pretty simple, not very complicated, very easy to write. Let's write the helper methods now. If list dot length equals to 0 or list equals to null. Corner cases are very important. Never forget to write them. And let's write a helper method return, which is our merge sort logic. List, which is the lower values. 0th index is the first pointer, and what is the highest value? List dot length -1. And whatever the result of this helper method, it is our final answer. Private list node helper, and it accepts an array of list, integer low, integer high, and for the case if low is greater than high, what do? Return null. Corner case, never forget that, very important to write. Else if low equals to high, return list of low. Else what do? What we will do, we'll calculate the middle part, mid index. Low plus high minus low by 2 in order to avoid any overflow conditions. And let's find the left part by left part. How? So we'll invoke the helper method, and over the list low comma mid, and similarly we'll do it for the right part, and this time it will start from mid plus 1 till high, and now we will merge the two lists left and right. Merge left comma right. Yeah, we are done with the logic, and let's quickly code this up, run this up. Looks good. Let me just submit it. Accepted. What is the time complexity of this approach? The time complexity of this approach is L1 plus L2. So since we are summing up these two elements, the time complexity of this method would be the merge sort time complexity is k log n log n, because we are always dividing it into two groups and then performing the merge operation. So on the similar basis, the time complexity would be k log k, where k is the size of the input list. Now let's walk up to the second approach, where I'll be using priority queues for solving this question using BFS methods. I'll share both the codes in my Git repo. Let's start with the second approach, which is the priority queue approach, or the min heap slash BFS, similar kind of approach that we have built, where we always pick out the minimum of all the possible elements that are there in the priority queue and attach it to the answer list. Let's start. List node if, first of all, the corner cases, if list equal to null or list dot length equals to 0, that means there is nothing in the input, return null. Otherwise, let's define the comparator list node over the list node, and let's call it custom compare new comparator, and it will accept we will override its public method public int compare. It will accept two parameters, list node A and list node B. How will we compare? A dot val minus B dot val. We call it the min heap technique, the min heap comparator. And let's define the priority queue. What will be the generic type? List node, and let's name it PQ priority queue. And what will it accept? The custom comparator. Let's add all the lists that are there in our list nodes in the priority queue. List node list, iterating over lists array. If list is not equal to null, one of the safety checks, pq.offer list. So we defined the comparator. First of all, we added the safety checks, corner cases. Defined the comparator which accepts two list nodes and return the one with the lower value. Defining the definition of the priority queue and adding all the elements that are there in the input list into the priority queue. Let's prepare for our answer list now. How? Remember the dummy pointer technique, -1 and list node t for iteration over the answer list. And let's write now the similar to what we write in BFS. P dot is empty till the time it is not null. What we'll do, we'll pull out the one with the lowest value, holding the lowest value list node, pq dot poll. So it will give us the list node lowest value node, and we'll attach t dot next to lowest value node. We'll increment t to the next pointer. And now if lowest value node dot next is not equal to null, that means we have not reached the end of any of the list. We'll add it back into the priority queue. Pretty simple. Now let's return dummy.next, which is a new head of merged lists. Compilation error, sorry for that. Again a compilation error. Hope this time it passes. It passed. Accepted. What is the time complexity of this approach? And the time complexity of this approach is equal to the standard time complexity of k log k, where you're sorting all the elements in the layer, where k stands for all the elements that are there across all the lists. Hope you liked it, and thanks for watching it.